Here we want to look at an example of the motion of an object along a curved path using the Cartesian coordinate system. So we know that if an object is traveling along a curved path, we could keep track of its motion by using a position vector relative to a reference. So this position vector will keep track of position vector r, will keep track of the position of the particle. In this particular example, r is not given, but rather we are given the velocity as a function of time. So velocity is given as three components here, 2t cubed I, so that's the x component of velocity, plus 3t squared j, that's the y component, and the z component is 8t minus 2k. And let's close this. So this was our x-axis right here. Okay, so given this velocity as a function of time, we know that at t equals 0, the position of this particle is at 0, 0, and 0, so it's at the origin. And what we want to find is acceleration of this guy, magnitude of acceleration at t equal 1, and also position at t equal 1. Now position means x, y, and z, the coordinates of this particle at t equal 1. So this is really a trivial problem. First of all, if you want acceleration, if you have velocity, you just have to go ahead and take the derivative of velocity. We could do that. So we notice that derivative of 2t cubed is 6t squared. That's the x component of acceleration. Then we have 6t j, y component, and then just a constant 8. And then if you go ahead and plug in t equal 1 into this equation, our acceleration vectorially becomes 6i plus 6j, and then notice that the z component is not a function of time, 8k. And if you want to find the magnitude, all we have to do is do a square root of x component squared plus y component squared plus z component squared, and that becomes about 11.66. We didn't identify a unit. Let's say the unit of velocity was given in meters per second, so acceleration becomes meters per second squared. So this 11.66 is the magnitude of acceleration. Now, what we have to do to find position at a given time is first integrate velocity and then try to figure out the constant of integration. So if velocity is given, let's go to the next page. Since velocity is the rate of change of position vector r, and r actually defines position, it's the position vector, that would be the integral of velocity with respect to time. So we go ahead and integrate the velocity. Remember, velocity was given as 2t cubed I plus 3t squared j plus 8t minus 2k. If we integrate this with respect to time, and keep in mind that we have constant of integration, so we end up getting 1/2 t to the power 4 plus a constant c1 I, right? So this is power 4, and plus t cubed plus another constant, we call it c2, and then finally 4t squared minus 2t plus another constant, call it c3, and this is running out of space k. But since at t equals 0, our x, y, and z position are 0, then c1 is going to be 0, c2 is going to be 0, and similarly c3 is going to be 0. Therefore r, our position vector r, becomes just 1/2 t to the power 4i, and t cubed j, and then finally a 4t squared minus 2t k. So this is position vector r as a function of time. So then at t equal 1, r becomes half I, a 1j, and a 2k. Therefore, the position of this particle is, the coordinates of it would be 1/2, 1, and 2 at t equal 1.